Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. I have prepared a training course on pumping system in refineries and chemical plants, which will be beneficial for those who are working in oil and gas refineries and chemical plants. After completing this course, you will be able to review the history and design of pumps. Describe the scientific principles associated with centrifugal pump operation and identify key components. Describe the operation and maintenance of positive displacement pumps. List the various types of rotary pumps. Describe the basic components and operation of screw pumps. Explain how rotary gear pumps operate. Describe the basic components and operation of sliding and flexible vane pumps. Describe the basic components of a Lobe pump. List the various types of reciprocating pumps. Explain the operation of diaphragm pumps. Describe the operation and design of piston pumps. Describe the scientific principles associated with the operation of plunger pumps. Start up and shut down a positive displacement pump. Start up and shut down a centrifugal pump. Troubleshoot typical problems associated with the operation of centrifugal and reciprocating pumps. Before starting the course, let us have a look at key terms. Acceleration head is the fluctuations of suction pressure created by the intake stroke of a reciprocating pump. Axial pump is a dynamic pump that accelerates fluid in a straight line. Cavitation is the formation and collapse of gas pockets around the impellers during pump operation, results from insufficient suction head or height at the inlet to the pump. Centrifugal pump is a dynamic pump that accelerates fluid in a circular motion. Diaphragm pump is a reciprocating pump that uses a flexible diaphragm to positively displace fluids. Discharge head is the resistance or pressure on the outlet side of a pump. Dynamic is a class of equipment such as pumps and compressors that convert kinetic energy to pressure, can be axial or centrifugal. Head is described as pressure at suction times 2.31 divided by specific gravity. 1 psi is equal to 2.31 feet of head. Impeller is a device attached to the shaft of a centrifugal pump that imparts velocity and pressure to a liquid. Lobe pump is a rotary pump that uses kidney bean-shaped lobes to displace and transfer fluid. Mechanical seal provides a leak-tight seal on a pump, consists of one stationary sealing element, usually made of carbon, and one that rotates with the shaft. Net positive suction head NPSH is the head pressure in feet of liquid necessary to push the required amount of liquid into the impeller of a dynamic pump without causing cavitation. Net positive suction head available NPSHA is a term used to indicate the required pump suction pressure so the pump can operate properly. It is defined as atmospheric pressure, converted to head, 1 static head 1 surface pressure head 2 vapor pressure 2 frictional losses. Net positive suction head required NPSHR is the minimum NPSH necessary to avoid cavitation. The NPSHA must be greater than or equal to the NPSHR, expressed as NPSHA greater than or equal to NPSHR. It is the reduction in total head as the liquid enters the pump. Piston pump is a reciprocating pump that uses a piston and cylinder to move fluids. Positive displacement is a class of equipment such as pumps and compressors that move specific amounts of fluid from one place to another, can be rotary or reciprocating. Pressure relief valve is used to relieve excessive pressure on the discharge of a positive displacement pump. Priming is becoming filled with fluid. Pulsation dampener is a device installed close to a pump, in the suction or discharge line, to reduce pressure variations. Reciprocating pump is a positive displacement pump that uses a plunger, piston, or diaphragm moving in a back-and-forth motion to physically displace a specific amount of fluid in a chamber. Rotary pump is a positive displacement pump that uses rotating elements to move fluids. Screw pump is a rotary pump that displaces fluid with a screw. Slip is the percentage of fluid that leaks or slips past the internal clearances of a pump over a given time. Specific gravity is described as the ratio between the density of a given liquid to the known density of water, or the density of gases to the density of air. The specific gravity of water or air is 1. Vane pump is a rotary pump that uses flexible or rigid vanes to displace fluids. Vapor lock is a condition in which a pump loses liquid prime, and the impellers rotate in vapor. Pump applications and classification. Refineries and chemical plants use pumps to move liquids. Pumps are used in a variety of applications and processes, including refrigeration, automobiles, home heating systems, and water wells. The liquids moved by a pump vary from liquid sodium and liquid potassium for cooling nuclear reactors to domestic drinking water systems. In some situations, pumps are not needed to transfer liquid. In picture, gravity transfers the liquid into tank 4.02b. In picture, a pump is needed to move the liquid. In general, pumps can be classified as dynamic or positive displacement as shown in picture. Both classes are designed to transfer liquids, but the way the transfer is accomplished is different. Dynamic pumps accelerate liquids axially in a straight line or centrifugally in circles. They are operated at high speeds to generate large flow rates at low discharge pressures. Pressure moves the liquid through the piping and equipment system. Positive displacement, PD, pumps transfer liquids by using a rotary or reciprocating motion that displaces liquid on each rotation or stroke. They are used in processes that require specific amounts of fluid to be delivered. The operation of positive displacement pumps is significantly different from that of dynamic pumps. Positive displacement pumps transfer specific amounts of fluid no matter what the discharge pressure is, whereas the amount of fluid transferred by dynamic pumps is greatly affected by discharge pressure. Rotary pumps deliver a specific amount of fluid with each rotation of screws, gears, vanes, or similar elements. Reciprocating pumps move fluids by drawing them into a chamber on the intake stroke and pushing them out of the chamber with a piston, diaphragm, or plunger on the discharge stroke. The first reciprocating pump, invented by a Greek, Ctesibius, in about 200 BCE, was used to pump water. Around the same time, Archimedes, a Greek mathematician, invented the first screw rotary pump. The first true centrifugal pumps were not invented until the 1600s by the French inventor Denis Papin. Papin's straight vane centrifugal pump design was improved in 1851, when a British inventor, John Apple, designed a curved vane pump. Internal slip. Slip is defined as the percentage of fluid that leaks or slips past the internal clearances of a pump over a given time. Slip also can be defined as the difference between how much liquid a pump can move and how much it actually does move. Because of differences in design, positive displacement pumps and centrifugal pumps respond differently to slip. A centrifugal pump can have as much as 100% slip if the discharge valve is closed. This principle can be illustrated by following the path of liquid as it enters a centrifugal pump with an open discharge valve. As fluid moves from the suction inlet into the impeller, flow is accelerated into a discharge chute known as a volute. The volute is a specially designed chamber that widens within the pump. Shutting the discharge valve stops flow to the process unit, but circulation within the pump continues. As the impeller turns, fluid is accelerated into the large volute discharge. Circular motion, clockwise, is sustained in the volute and discharge pipe up to the discharge valve as shown in picture. Fluid friction within this area begins to heat up the liquid. Operators should keep this principle in mind if the liquid being pumped is close to its boiling point. When the liquid vaporizes, it expands and gets hot. This process can create tremendous pressure that will damage the pump. Positive displacement, PD, pumps are designed to have minimal slip characteristics. There are physical laws that state that two separate bodies cannot occupy the same space at the same time. Positive displacement pumps are designed to displace exact fluid volumes with solid objects, such as pistons or gears. When the discharge valve is closed on a PD pump, the following conditions exist. Very little, if any, slip is occurring within the body of the pump. Fluid pressure increases with every stroke. Fluid pressure is transferred equally to all isolated parts. The pump or discharge pipe can be damaged if a relief valve is not provided. Dynamic pumps. Dynamic pumps are classified as centrifugal or axial. Centrifugal pumps operate on the principle of centrifugal force. A spinning impeller inside a shell casing propels liquid outward. Fluid velocity is accelerated inside the shell of the pumps and liquid quickly moves toward the discharge port. This picture illustrates the different types of impeller arrangements in a centrifugal pump. The axial pump utilizes a similar spinning motion to propel liquid, but the liquid moves in a straight line. This motion is directionally different from the centrifugal pump's outward movement. Centrifugal pumps. Centrifugal pumps are used widely in chemical processing plants and refineries. The primary principle used by centrifugal pumps is centrifugal force. As liquid enters the suction eye of a centrifugal pump, it encounters the spinning impeller as shown in picture. The liquid is propelled in a circular rotation that forces it outward and into the volute. Centrifugal force and volute design convert velocity energy to pressure. As the liquid leaves the volute, it slows down, building pressure. Diffuser plates also can be added to the impeller and volute area to slow down or change the velocity of the liquid. Basic components. The basic components of a centrifugal pump are shown in picture. The outer casing is designed to enhance fluid flow. It contains the fluid, forms a volute, and holds external and internal parts together. Typically, it comes in two parts separated by a gasket and bolted together. An axially split casing is split parallel to the pump shaft. A radially split casing is split perpendicular to the pump shaft. A drain on the bottom of the casing allows liquid to be drained from the pump. The volute is a gradually widening cavity inside the casing of a pump. The inlet is sometimes referred to as the suction eye. Fluid comes into the center of the impeller and is spun toward the outside of the volute. The inlet line is designed to run when primed, full of liquid. The outlet line receives the discharge from the pump volute. Because the discharge line is wider than the inlet volute, fluid velocity slows, creating pressure. The impeller is a circular device attached to the shaft. The impeller resembles a wheel of curved blades that rotates around the shaft, spinning liquid from the eye, center of the pump, to the outer casing of the pump. This liquid enters the tapered neck of the volute before exiting the pump into the discharge line. The driver is an electric motor, fixed speed or variable speed, or a steam turbine. A manufacturer's nameplate lists the important information specific to the motor, phase, horsepower, manufacturer, and type. Radial bearings along the shaft minimize side-to-side movement. Thrust bearings eliminate axial movement along the shaft. Between the bearings and seals, a loose-fitting flinger ring mounted on the shaft conveys lubricant onto the bearings. The ring rotates on the shaft, but at a lower speed. Mechanical seals installed where the rotating shaft enters the casing minimize or stop leakage from the internal components of the pump. Mechanical seals are composed of a stationary face and rotating face that fit closely. Seal faces may require lubrication or cooling. They require very low maintenance, have a reasonably long life, and have very little product leakage. The stuffing box and packing gland hold packing firmly against the shaft and casing. A slight bit of internal leakage keeps the packing lubricated and cool. The packing material, located between the casing and the shaft, consists of rings composed of flexible material coated in graphite or Teflon. The packing needs to be replaced frequently. Where rings minimize leakage between the internal discharge and suction of the pump. Because the rotating impeller does not come into contact with the stationary casing, a void exists between the suction and discharge areas. Properly positioned wear rings minimize this leakage. If the wear rings are mounted on the pump's impeller, they turn with the impeller and are referred to as impeller wear rings. If the wear rings are mounted to the casing, they are stationary and are referred to as casing wear rings. Pump design. Centrifugal pumps come in a variety of designs and applications. Vertical or horizontal refers to shaft position, single stage or multiple stage refers to the number of impellers, single or multiple suction inlets, volute or diffuser, axial flow, radial flow, or mixed flow, and open, semi-open, or closed impeller design. Horizontal pumps are the most common type found in industry. However, vertical pumps are more compact, winterize better, and have a lower installation cost. Vertical pumps work well with liquids that are near their bubble point temperature. The lower impeller usually is located below ground level, which provides additional net positive suction head available, NPSH. The terms horizontal and vertical refer to the position the shaft occupies in relation to the ground as shown in pictures. This direction indicates how impellers rest in the device. Another term used in the operation of a centrifugal pump is net positive suction head required, NPSH. Net positive suction head required is the minimum NPSH necessary to avoid cavitation. The NPSH must be greater than or equal to the NPSH, expressed as NPSH $NPSH. It is the reduction in total head as the liquid enters the pump. Most centrifugal pumps have a single suction inlet. In applications where the pumping volume is very high or source parameters vary significantly from destination parameters, pumps that have more than one suction inlet are used. In applications where the difference is minimal, single suction inlet pumps are used. Impeller design. The simplest type of centrifugal pump, a single-stage pump, has only one impeller. Multi-stage pumps have more than one. The impeller design comes in three basic types as shown in picture. On the open impeller, vanes are connected only to the shaft. The open impeller is self-cleaning but does not have the structural support of a semi-open or closed impeller and is less efficient at producing pressure. On the semi-open impeller, the vanes are horizontally attached to a plate for structural support. On the closed impeller, the vanes are sandwiched between two plates or shrouds. This is the strongest and most efficient design, but it is designed for use with clear liquids only. It is the most common type of impeller in industry. Advantages and disadvantages. The chemical process industry typically uses centrifugal pumps that operate between 1,200 and 8,000 RPM. In modern manufacturing, centrifugal pumps are used more than positive displacement pumps because they are cheaper and require less maintenance and space. Another attractive feature of centrifugal pumps is that they will operate with a constant head pressure over a wide capacity range. In addition, it is easier to change the element, impeller versus piston, on a centrifugal pump than on a positive displacement pump, and it is easier to change the driver. A final advantage is the adaptability of the selected driver variable horsepower and fixed or variable speed. Centrifugal pumps do have some disadvantages. They are not self-priming and respond poorly to viscous materials or variations in suction pressures. This picture illustrates how a centrifugal pump transfers liquid from one vessel to another. Head pressure. In a centrifugal pump, fluids must be pushed, not sucked or pulled, into the impellers. Suction head is a term used to describe the pressure required to force liquid into a pump. Most processes are designed so that the suction pressure is sufficient to run the pump without cavitation, that is, the formation and collapse of gas pockets around the impellers. A centrifugal pump must be primed, full of liquid, or liquid full, before the pump can be started. During operation, a centrifugal pump will artificially create a low pressure area in the suction eye. If the suction pressure is not carefully controlled, the low pressure could cause the liquid to boil. Boiling creates the condition called cavitation. Net positive suction head, NPSH, usually is calculated in feet of liquid. For example, if a pump took suction off the bottom of a 20-foot open tank with a liquid level of 10 feet, the static head would be 10 feet. This same principle can be applied to the discharge head on a pump. If the tank is closed, the vapor pressure of the liquid must be taken into consideration. Vapor pressure is closely related to the boiling point of a liquid. Heat affects vapor pressure by increasing molecular activity. NPSH is the minimum rating at which a centrifugal pump operates. Another problem associated with centrifugal pump operation is vapor lock. Vapor lock is a condition in which a pump loses liquid prime, and the impellers rotate in vapor. Bled valves are located on the pump to remove air from the system. The pump must be shut down and air bled out before it will operate properly. Factors that affect suction head pressure are temperature, viscosity, a fluid's resistance to flow, level of liquid in the suction system, restriction in the suction line, and flow rate through the line. Solutions to insufficient NPSH are smaller horsepower, lower speed, lower NPSH requirements, larger diameter suction line, greater feed tank level or pressure, and cooler feed. Determining differential head. A centrifugal pump requires a certain amount of back pressure, differential head, in order to operate efficiently. The following exercise should illustrate the relationship between NPSH and the required differential head. It will also illustrate how piping changes and equipment modifications will affect the operation of a pump. A centrifugal pump should be viewed as having a set of conditions on the suction side and a wide array of variables on the discharge side. In the following depropanizer example, liquid propane is pumped from the reflux drum to the depropanizer column as shown in picture. On the suction side of the pump, a liquid level of 16 feet plus an operating pressure of 180 psi exists on the suction eye of the pump. The discharge of the pump is lined up through a series of gate valves, a check valve, a filter, an orifice, and a control valve. The discharge line contains a liquid leg of propane, 68 feet high. The depropanizer column operates at a pressure of 200 psi at a temperature of 90 degrees Fahrenheit or 32 degrees Celsius. The flow rates are 300 gallons per minute, GPM, normal and 340 GPM maximum. The required differential pressure of 318.7 psi takes into consideration all of the variables associated with the operation of the pump. Under these conditions, the centrifugal pump will operate efficiently. Pressure changes on the suction or discharge side of the pump will affect unit operation. Pressure is defined as force or weight per unit area, force, in pounds, divided by area, in square inches, equals pressure, in pounds per square inch. Atmospheric pressure is produced by the weight of the atmosphere as it presses down on an object resting on the surface of the Earth. Pressure is directly proportional to height. The higher the atmosphere, gas, or liquid, the greater the pressure. At sea level, atmospheric pressure equals 14.7 psi. Pressure calculations are easily performed using common standards. The primary standard for liquid calculations is water. For example, the weight of water can be used to determine the specific gravity of a liquid. Specific gravity is the ratio of the density of a solid or a liquid to the density of water or the ratio of the density of a gas to the density of air. Density is weight per unit volume. To calculate the pressure produced by 1 feet cube of water, we need to use the equation pressure equals force divided by area. 1 cubic foot of water weighs 62.4 pounds. The surface area of 1 feet cube is 12 inches. Times 3 12 inches. Equals 144 inches. For water, 62.4 divided by 144 is equal to 0.433 psi. For each additional foot of water, an additional 0.433 psi can be added. Expressed another way, psi times 2.31 equals head, foot, or head, foot, divided by 2.31 equals psi. A common equation for determining pressure is height times 0.433 times specific gravity equals pressure. To calculate the required differential head, h, we need to know the specific gravity of propane. Specific gravity of propane equals 0.485. The unknown factor is delta P, differential pressure. To solve for delta P, we must pay close attention to the variables that contribute to pressure changes in a process system. Head, H, equals delta P times 2.312 divided by specific gravity. The absolute suction pressure factors that are involved are: reflux drum equals 180.00 psi, elevation 16 feet equals 3.36 psi, friction of piping is minus 0.50 psi, friction of valves is minus 0.20 psi. It gives us 182.66 psia, and after subtracting 14.7 we will get 167.96 psig. The absolute discharge pressure factors are: depropanizer tower 200.00 psia, elevation 68 feet equals 14.29 psi, friction of piping is 3.00 psi, ration of valves is 2.00 psi, friction of control valve is 9.00 psi, for check valve it is 1.00 psi, for orifice 1.20 psi, for filter 13.00 psi. In total will be 243.49 psia or 228.79 psig. Now we can solve for delta P equals 228.79 psig minus 167.96 psig equals 60.83 psig and plug that value into our equation for head. H equals delta P times 2.31 divided by specific gravity. Multiply in a standard safety factor of 1.1. The required differential head is 318.7 feet. Total head. Look again at picture. The fluid in TK 4.02a appears to be at the same level as the fluid in TK 4.02b. The pump inlet and discharge are full, and the pump has been bled down and is liquid full. With both the suction and discharge valves open, indicated by the bow tie-shaped symbols, fluid levels equalize in the tanks. A pump is needed to transfer additional liquid into TK 4.02b. As the level increases in TK 4.02b, the discharge head, pressure in the discharge line, increases proportionally to the liquid level in the tank. Total head is equal to the discharge head minus the suction head. Operators should be aware that a centrifugal pump stops moving liquid if the discharge pressure gets too high. As discharge pressure increases, the liquid velocity slows down and even stops, and centrifugal force decreases, perhaps reaching zero. Pump curves. Centrifugal pumps are designed to work in specific services at specific rates. The best operating condition for a pump usually is indicated on the pump's efficiency curve. The efficiency curve includes several values: flow rate, in GPM, total head in feet, discharge head minus suction head, sometimes called differential head, pump efficiency, required pump horsepower, and pump NPSH. Because pumps are not always operating under their optimal conditions, they are designed to work across a range of rates and liquid properties. The operating parameters, driver horsepower, impeller size, liquid properties, pump efficiency, pump capacity and head, NPSH requirements, and so on, are all shown on a graph known as the pump curve as shown in picture. When there is a problem with a pump's performance or a change in the service, the pump curve is one of the first documents consulted. Manufacturers typically include pump curves with their products so that engineers and operators can refer to them before changing or redesigning a pump system. If the pump is operated at higher rates, efficiency decreases, and the pump could be damaged. Cavitation. Cavitation occurs when suction pressure drops below NPSH. At this point, the liquid vaporizes and forms gas pockets inside the pump casing. As these pockets form and collapse, the pump can be severely damaged. Operators easily can identify a pump that is cavitating. The sound of a cavitating pump closely resembles the noise you would hear if steel ball bearings were dumped into a pump suction line. The operator also can expect to see rapid swings on the discharge pressure. Cavitation sends slugs of liquid and vapor through the pump. Each slug has an impact on the internal components of the pump. Serious damage will occur if this problem is not resolved quickly. Affinity laws. Relationships, called affinity laws, exist among a centrifugal pump's speed, capacity, head, and power. The capacity of a centrifugal pump is linked directly to its speed, or RPM. Total head is proportional to the square of the speed. Consumed power is proportional to the cube of the speed. Pump selection chart. Modern industrial manufacturers use a pump selection chart when they are engineering a new process. The chart is set up with a horizontal axis that identifies capacity in GPM and two vertical axes that identify head in feet of liquid on the left and pressure in pounds per square inch on the right. Construction materials. Centrifugal pumps typically are manufactured with cast iron internal components and cast steel external cases. They can be made of most alloys as needed to cope with the nature of the liquid being pumped. Factors that affect suction and discharge. Operators need to be aware of the number of process variables that exist inside a system, including upstream and downstream vessels, valves, filters, piping, discharge head, and suction head. Each of these factors affects how efficiently a pump will operate. This picture illustrates a tank-to-ship transfer. Single and multi-stage pumps. The terms single-stage and multi-stage are used to refer to the number of impellers a centrifugal pump uses. As flow enters a multi-stage pump, it enters the suction eye of the first stage impeller. As the spinning impeller accelerates the fluid, it graduates into the suction of the next stage, where it is accelerated even more. At each stage, the pressure and fluid flow increase until the fluid reaches the discharge chamber. When a designer builds a multi-stage pump, the concept of thrust must be considered. The suction side of an impeller exerts a small force on the shaft. The discharge of the impeller exerts a significant amount of thrust on the rotor. Collectively, the sum of the forces along the shaft is tremendous in a multi-stage pump. There are two ways to minimize thrust. One way is to use a balance device, a hydraulic system that connects the pump suction to the discharge end of the pump. The system is composed of a discharge side balancing drum, a balance line, and a low-pressure reservoir behind the drum. Another way is to align the impellers in opposite directions. Opposite alignment maintains even thrust along the shaft. Multistage pumps must never be operated with the discharge valve closed. Usually, a minimum flow system is designed into the piping so that there is always sufficient flow through the stages to protect them from damage.
How does a centrifugal pump work? Centrifugal pumps are used to pump water, oil, and other liquids. Let's try to understand why these pumps are designed to carry out the task of transporting liquids successfully. The main elements of a centrifugal pump are the casing and the impeller, which drives the liquid. The impeller is mounted on a shaft. The shaft can rotate on bearings. The power is transmitted from the motor, most often an electric motor, to the shaft. The impeller of the pump rotates, together with the shaft. The vanes in the impeller act on the liquid and make it rotate. The liquid particles are accelerated. As a result of the impact of the vanes, the energy of the liquid flow is increased. The accelerated liquid particles enter the volute, which converts part of the velocity into pressure. The diameter of the passage section of the voltage and the discharge nozzle gradually increases. The fluid velocity decreases, and the pressure, according to Bernoulli's law, increases. Three main types of impellers are used in centrifugal pumps: closed with back and front discs, vanes and fairings. Semi-open with the vanes are free on the front side. Open with the vanes free on both sides. If bearings support only one side of the shaft, the pump is called a cantilever pump. It is a versatile design that is used in small and medium-sized pumps. A heavy impeller cannot be cantilevered. In this case, the shaft is mounted on bearings and the impeller is placed between them. This construction scheme is well suited for double suction impellers where the vanes are placed on both sides. A double suction impeller allows liquid to enter the impeller blades from both sides. Thus, we have two pumping units without significantly increasing the weight and dimensions of the pump. This scheme is relevant for pumps with high capacities because the pumping units are installed parallel. Multi-stage centrifugal pumps. By installing pumps in series, the head of the liquid can be increased in the system. Pumps installed in series can be combined by placing several impellers in the same casing. The liquid will go from the first impeller to the second one, from the second impeller to the third one, and so on. Using a multi-stage arrangement can increase the head of the pump many times over, as the impellers are mounted in series, and each of them increases the head. In multi-stage pumps, different impellers can be used. For example, a screw centrifugal pump has an auger on the first stage and a centrifugal impeller on the second stage. When the pump is running, the liquid flows continuously into the pump casing through the suction nozzle. But what happens if there is no liquid in the pump? For example, when the pump is first switched on, the pump casing will be empty. For the liquid to fill the pump, the pressure in the pump casing has to be lower than the atmospheric pressure. Then, the atmospheric pressure will cause the liquid to fill the casing. To reduce the pressure in the pump, some of the air has to be pumped out of the casing. Is an ordinary centrifugal pump able to do this? The answer is no, because the particles move in the pump due to inertia, which depends on mass. The mass of air particles is much lower than that of water particles, so it is impossible to pump air at speeds that a centrifugal pump operates at. For this reason, centrifugal pumps must be primed before switching on, either through a special channel in the casing or through the discharge nozzle.
Axial pumps. Another way to accelerate and transfer fluid is to push it axially, or in a straight line. Axial pumps, as shown in picture, are designed to provide this special feature. A common example of this principle is a boat motor. The motor turns a set of blades, forcing water to accelerate along a straight line. An axial pump operates using this same principle. Most axial pumps are located in an elbow on a piping run. The driveshaft extends through the elbow and into the process flow. A propeller is located on the process end of the driveshaft. The propeller is sized to fit the inside diameter of the pipe. The belading is engineered to pull fluid axially down the shaft. A mechanical seal prevents leakage where the shaft penetrates the pipe elbow. A specially designed thrust bearing prevents axial movement of the shaft. Heavy-duty radial bearings support the pump shaft and prevent radial movement. Some axial pumps have thrust-bearing oil coolers. An optional safety seal oil system or thrust-bearing lube system is available for some models. The motor is mounted just outside the elbow on a pad that allows for exact driveshaft lineup. A coupling securely connects the motor to the pump. Axial pumps can be mounted vertically or horizontally. Axial pumps are frequently found in pipeline service and as the primary transfer device on loop reactors. Drive options include direct, variable, and belt drive between 7.5 and 2,000 horsepower. Design pressures vary between 300 and 1,500 psi. Design temperatures range from 250 degrees to 650 degrees Fahrenheit or 245.55 degrees Celsius to 343.33 degrees Celsius. Jet pumps. Jet pumps, as shown in picture, take their name from the way they transfer liquids. A specially designed jet is engineered to utilize the Venturi effect. Jet pumps are frequently used to lift water from wells over 200 feet deep. When a water well is set, a hole is drilled down to the water table. A polyvinyl chloride (PVC) screen is connected to a PVC water pipe that is pushed down the open hole. The pipe is allowed to extend a few feet above ground level. Water passes through the screen and into the pipe. Pressure in the water pocket causes the water level to pass through the screen and up the pipe. The water level will typically stop before it reaches the top of the pipe. The process of lifting the water out of the pipe is the function of the jet pump. The different parts of the jet assembly and drop pipe include a foot valve, nozzle, venturi, suction, and discharge. During installation, a foot valve or check valve is securely attached to the bottom of the jet. A leather seal is located between the check and the jet. The jet is secured to the drop pipe and lowered into the water pipe casing. A specially designed adapter is used to connect the center drop pipe to the outer casing. The adapter provides a base upon which the vertical centrifugal pump can be mounted. During operation, water is forced back down the void between the center drop pipe and the outer casing. As water is pumped back into the well casing, the foot valve slams shut. A small opening in the jet provides access back to the suction of the pump. A Venturi effect occurs at the jet as pressure builds up in the casing. As pressure increases in the casing, velocity increases across the jet. A low pressure zone is established inside the drop pipe as water quickly flows up toward the pump. A back pressure regulator holds pressure inside the pump until it reaches operating conditions. When pressures reach operating conditions, water flow is divided as some water recirculates down the casing and the excess flows to a storage tank. Another common jet pump arrangement includes a jet assembly and a centrifugal pump. The jet assembly forms a suction chamber that creates a vacuum when a stream of high-velocity water flows through a jet. The jet assembly is composed of two major parts, a nozzle and a Venturi tube. The nozzle directs high-velocity water into the Venturi tube or diffuser. As the high-velocity water exits the nozzle and enters the diffuser, it slows down, creating pressure. The primary purpose of the diffuser is to convert water velocity to pressure. Positive displacement pumps. Rotary and reciprocating pumps are the two major classifications of PD pumps. Rotary pumps displace liquid with rotary motion gears, screws, vanes, or lobes. Reciprocating pumps displace fluid with a diaphragm, piston, or plunger that moves back and forth. You must be cautious during pump operation. A PD pump should never be blocked on the discharge side until the pump is turned off. Equipment and personnel can be severely damaged if the discharge side is blocked while the pump is on. Most PD pumps are provided with pressure relief valves to prevent damage. Rotary pumps. Rotary pumps are PD pumps that transfer liquids by using a rotary motion. The drive shaft turns the rotary elements inside a leak-tight chamber that has a defined inlet and outlet. Engineering design requires close running clearances between the rotating elements and chamber wall. Rotary pumps have very little internal slip. This type of pump is the most widely used positive displacement pump. Rotary pumps are used to move the more viscous type of fluids, heavy hydrocarbons, syrup, paint, and slurries. Rotary pumps combine the rotary motion of a centrifugal pump and the positive displacement feature of a reciprocating pump. Rotary pumps come in four main types: screw, single and multiple, gear, internal and external, vane, sliding and flexible, and lobe. Single-screw rotary pumps or progressive cavity pumps. A progressive cavity, or PC, pump as shown in pictures consists of only one moving part, the rotor. The rotor turns inside an elastomer-lined stator. When the self-priming rotor turns, cavities, or voids, are formed between the rotor and the stator. These voids progress axially from the suction casing to the discharge outlet. During operation, the cavities fill with fluid. Progressive cavity pumps provide high suction, extremely low shear, and smooth pulsation-free operation. These features are important where turbulence affects fluid composition. The PC pump is ideally suited for metering operations. Typically, this type of pump is used for heavy or viscous fluid service. The solid content of the process fluid does not affect the effectiveness of a PC pump. Progressive cavity pumps can be found in a variety of applications. Operating conditions include pressures up to 1000 psi, flow rates to 950 GPM, and viscosities of over 1 million centipoises. Rotor and stator. The rotational speed of the rotor and the total volume of the cavities determine PC pump flow rate. The rubbing velocity determines rotor and stator life. If the space between the rotor and stator is small, a high degree of rubbing velocity is created. Rubbing velocity is a major factor in the life of the stator. The stator can be replaced after it is worn out. The rotor is typically made of high-chrome tool steel that resists particle abrasion. The stator is manufactured by extruding molten elastomer under high pressure into a heavy metal stator tube with an inner rotor core. When the molten elastomer cools, the core is removed. The stator tube can be threaded on each end for easy installation over the rotor, or it can be connected with 4 tension rods. Universal joints. The universal joint, U-joint, transmits torque from the drive shaft to the rotor. The PC pump's U-joint is located in the suction housing of the pump. As process fluid flows around the U-joint, dead zones are eliminated. The rotor in a PC pump turns about 3 different rotation centers, that is, it has about 3 curves. Seals and bearings. The PC pump uses mechanical or soft packing to prevent leakage. The bearing housing is located on the drive shaft end of the pump. Large roller bearings designed to handle excessive loads protect the drive shaft as it transmits torque through the bearing housing. Because of this unique design, PC pumps can be adapted to use belt or direct drives. Multiple screw rotary pumps. Multiple screw rotary pumps can be used in a variety of applications. They have either 2 or 3 screws. The versatile, heavy-duty, self-priming, 2-screw pump has been in service since 1934. The special design of the pump elements enables the 2-screw pump to provide high flow rates and excellent suction and to pump virtually any fluid. A 2-screw pump has 2 rotors, a power rotor and an idler rotor. A set of external timing gears and bearings allows the screws, the rotors, to turn in unison without making contact with each other. This feature allows the pump to transfer any fluid regardless of abrasiveness, lubricity, or viscosity. In addition, because the screws do not touch, the pump can run empty without damaging the system. This feature makes it an ideal choice in tank stripping operations or in operations in which fluid suction pressure will vary. The twin-screw pump has a driving and a driven shaft, 2 screws, an external set of timing gears and heavy-duty bearings, and divided entry flow as shown in picture. As fluid enters the pump, it is divided into 2 equal streams and directed to the 2 ends of the shaft. The pumping action of the screws moves the 2 streams of process fluid in a straight line between the closely spaced rotors until they combine at the discharge port. In a 2 or 3 screw design, the direction of rotation of the power rotor will determine whether the inlet and outlet ports are located on the top or bottom of the pump. Because the 2 streams have equal, simultaneous flow paths, the rotating rotors are balanced. This unique design reduces bearing wear. Most 2-screw pumps require mechanical seals instead of soft packing on the suction side of the pump because of the large sealing area. 2-screw pumps typically operate at a speed of 3,500 rpm, flow rate of 8,800 gpm, inlet pressure up to 100 psi, discharge pressure up to 725 psi, and temperature up to 500 degrees Fahrenheit or 260 degrees C. The 3-screw pump consists of a power or driver rotor and 2 idler rotors as shown in picture. The power screw meshes with the idler screws during operation. The 3-screw pump is unlike the 2-screw pump in that the 3 screws touch. Each screw rotates easily on a set of heavy bearings. During operation, the self-priming screws rotate, creating voids that transfer fluid in a continuous, pulsation-free flow. A typical 3-screw pump does not need thrust bearings because of the balanced system. The engineering specifications allow this type of pump to be operated at speeds of up to 6,000 rpm, with pressures up to 750 psig, and flow rates around 600 gpm. Gear pumps. Gear pumps are similar to screw pumps in that they can be used in viscous service. Gear pumps typically can be found in 2 common types, external and internal. External gear pumps. External gear pumps have two interesting gears that rotate parallel to each other, allowing fluid to be picked up by the gears and transferred out of the pump as shown in picture. One of the gears is an idler gear, the other is attached to a driver and is referred to as the power gear. External gear pumps consist of two mating gears that rotate inside a casing. The rotation of the driver gear turns the idler, or follower gear, trapping fluid and displacing it. Typically, in this type of operation, the driver gear is mounted on top. Most operators refer to external gear pumps as constant displacement pumps. The discharge of an external gear pump remains constant unless the shaft speed is changed. The suction and discharge ports of an external gear pump are located on the opposite ends of the casing. When the pump is first started, air is forced out and into the discharge line. This process creates a low-level vacuum on the suction side. This vacuum causes fluid to enter the pump and be trapped between the gears. As the gears rotate, the fluid is swept around the housing and out of the discharge port. Internal gear pumps. A Danish-American inventor, Jens Nielsen, invented the internal gear (IG) pump in 1915. Process technicians refer to the internal gear pump as the gear within a gear pump. Internal gear pumps operate with only two moving parts, a power gear driving an internal idler gear as shown in pictures. When the power gear rotates, liquid enters the pump through the suction line. Since the pump is self-priming, the voids between the teeth of the power gear and the off-center idler gear fill with liquid. During rotation, liquid is separated by a crescent-shaped spacer. Liquid is pressed into the spaces above and below the crescent. As the gears rotate around the circular pump casing, the liquid is discharged out of the pump. The main components of an internal gear pump are a power gear or rotor, an idler gear, an idler pin, a driveshaft, a circular casing, the crescent, axial, and radial bearings, seals, and a relief valve. The idler gear rotates freely on a cylindrical idler pin. A main bearing and a second bearing on the free end of the shaft support the driveshaft. Soft packing or mechanical seals can be used on the pump. Internal gear pumps require very little maintenance. Design parameters on internal gear pumps include flow rates from 1 to 750 GPM, speeds up to 1750 RPM, temperatures up to 500 degrees Fahrenheit or 260 degrees Celsius, suction lift during operation up to 24 inches Hg vacuum, and differential pressures up to 250 psi. These pumps can be constructed of stainless steel for corrosive environments or of carbon steel or cast iron where applicable. The chemical processing industry uses internal gear pumps for chemicals such as acetone, acids, alcohol, alkalis, ammonium hydroxide, butadiene, polymers, resins, solvents, waxes, and xylenes. Internal gear pumps can also be magnetically coupled. Magnetic coupling eliminates the need for shaft seals. Sliding vane pumps. Sliding vane pumps as shown in picture consist of spring-loaded or non-spring-loaded vanes attached to a rotor, or impeller, that rotates inside an oversized circular casing. As the offset impeller rotates by the inlet port, liquid is swept into the vane slots. A small crescent-shaped cavity is formed inside the pumping chamber that the vanes extend into. As the liquid nears the discharge port, it is compressed as the clearance is narrow. The compressed liquid is released at the discharge port. The vanes on the pump are made of a softer material than the rotor and casing. A bevel on each vane closely matches the rounded edges of the chamber, and the softer vane material tends to wear evenly during the life of the vane. Sliding vane pumps typically are used with process liquids that have good lubricating qualities. Vane pumps are used in hydraulic systems, vacuum systems, and low-pressure oil systems. The typical vane pump has a capacity of 380 GPM and operates with a pressure differential of 50 psig. Flexible vane pumps. In a flexible pump system, the rotor is composed of a soft elastomer impeller, keyed to fit over the driveshaft that penetrates the pumping chamber. The pumping chamber is designed to provide good contact between the impeller and the inner chamber. Speeds are typically low since the rubbing velocity between the flexible vanes and chamber wall is significant. The impeller is centered in the pumping chamber. Flexible vane pumps are frequently used in vacuum service. Lobe pumps. Lobe pumps, as shown in picture, have two rotating lobe-shaped screws that mesh during operation. As the lobes turn, voids are created that compress liquids around the outside of the pumping chamber. In a lobe pump, a set of external timing gears and bearings allows the lobes to turn in unison without making contact with each other. This feature allows the pump to transfer a wide variety of fluids. Because the lobes do not touch, the pump can run empty without damaging the system. A lobe pump has a driving and a driven shaft, two lobes, an external set of timing gears, and bearings. As fluid enters the pump, it is divided into two equal streams. The pumping action of the lobes moves the process fluid in two streams around the lobes in the close tolerances between the casing and the lobes. The streams combine at the discharge port. The direction of rotation of the driver will determine the locations of the inlet and outlet ports on the pump. Lobe pumps are designed to provide high flow rates at low pressures. They have excellent suction and pump a variety of fluids. Reciprocating pumps. Reciprocating pumps, especially in small volume sizes, are positive displacement pumps very commonly used in the petrochemical industry. Reciprocating pumps are engineered to transfer small volumes of liquid at relatively high pressures. Most reciprocating pumps are self-priming and are operated at relatively low speeds because of the back-and-forth motion and the effects of inertia on internal components. Reciprocating pumps can deliver consistently high volumetric efficiencies even when applied to a variety of fluid types. They deliver liquid when a piston, plunger, or diaphragm physically displaces it. The diaphragm, piston, or plunger pushes the fluid as it moves back and forth inside a cylinder or housing. The suction system requirements for a reciprocating pump are similar to those of other pumps except for one important factor: acceleration head. Acceleration head takes into account the back-and-forth inertia that a reciprocating pump creates. Acceleration head is defined as the fluctuations of suction pressure created by the intake stroke of a reciprocating pump. The suction line of a reciprocating pump should be as short as possible. Excessive valves, bends, and fittings should be eliminated. The line should be large enough to deliver fluid velocities of 3 feet per second. Booster pumps typically can be added to the suction line to increase suction pressure. Diaphragm pumps. A diaphragm pump, as shown in picture, uses a flexible sheet, diaphragm, to displace fluid. This type of pump has a crankshaft or eccentric wheel attached to a connecting rod. The connecting rod is anchored firmly to the center of the diaphragm. The outer edge of the diaphragm is bolted or secured to the exterior casing. As the eccentric wheel, referred to simply as the eccentric, starts its rotation, the diaphragm connecting rod goes up and down. This reciprocating motion creates a pumping action that displaces fluid. The pumping chamber below the diaphragm is connected to suction and discharge lines. Spring-loaded valves open or close, depending on the pressure in the chamber. Diaphragm pumps have several advantages compared with most other types of pumps. They completely seal off the area between the diaphragm and the pumping cavity. They can be used to pump a variety of chemicals, and they can be used with low or negative suction head. Piston and plunger pumps. Reciprocating piston pumps, as shown in picture, use a piston and a back-and-forth motion to displace fluid. During normal operation, the piston pump has a suction stroke and a discharge stroke. The suction stroke occurs when the piston pulls out of the cylinder. This motion creates a low-pressure vacuum in the cylinder, causing the discharge valve to close and the suction line to open, filling the cylinder. On the return stroke or discharge stroke, the suction valve slams shut, and the fluid is forced out the discharge valve. This type of pump continues to operate no matter how high the discharge head is. The typical piston pump has a piston, piston ring, connecting rod, suction and discharge valves, casing and cylinder, and relief valve. Piston pumps are sealed internally and externally. Internally, the piston rings form a seal on the piston that can be seen only by tearing down the pump. The external packing seal is located where the piston rod enters the casing. Reciprocating plunger pumps, as shown in picture, operate with a back-and-forth motion and a device called a plunger to displace controlled amounts of liquid. The primary difference between a plunger pump and a piston pump is in the shape of the piston or plunger element and the way they seal. A piston pump has rings mounted on the piston that form a seal. The plunger on a plunger pump does not have moving rings. The plunger moves in and out of an O-ring or packing medium to form its own stationary seal. A major advantage of this type of sealing system is that the pump seals easily and can be replaced without major breakdown of the equipment. The basic components of a plunger pump are a plunger, crankshaft, connecting rod, pumping chamber, suction inlet valve, and discharge outlet valve. Double-acting design. The back-and-forth motion of a piston or plunger pump limits the smooth flow control characteristic of other pumps that do not have long suction intake and discharge strokes. Piston and plunger pumps tend to have pulsing or spurting flow rates. Using a double-acting design can compensate for this feature. A double-acting piston as shown in picture or plunger pump discharges and pulls in fluid on each side of the chamber on a single stroke. Because the double-acting pump discharges on each stroke, a more uniform flow rate can be maintained. Some engineering designs include pulsation dampeners to offset the problem of pulsing or spurting flow rates. The dampener should absorb cyclical flow variations. The pulsation dampener is a small pressure vessel with a diaphragm and a cushion of air to offset surges. Duplex design. Single-cylinder piston and plunger pumps have severe capacity limitations. Adding another cylinder compensates for this design flaw and doubles the flow capacity. Vacuum pumps. Operating systems that require pressures below atmospheric pressure use vacuum pumps. The typical vacuum pump falls under a variety of reciprocating, rotary, and dynamic categories. Vacuum pumps are frequently used in distillation operations, refrigeration, and air conditioning. Vacuum pumps are connected to the system to be evacuated with hoses, piping, or manifold systems. The connection is typically made in a location where liquid is not present. A knockout system is used to trap liquids before they can enter the pump. Some vacuum pumps have an oil seal inside the casing of the pump. During the evacuation process, the process flow is drawn into the pump and discharged. Contaminants are trapped in the oil, which may require frequent changing. The primary cause for pump failure is contaminated oil. When the pump is first started, it makes a gurgling sound as gas or vapors are drawn into it. A distinct rapping sound can be heard once the pump down is complete. The suction side of a vacuum pump should be closed before the pump is turned off because vacuum oil will be drawn into the internal pumping chamber. This problem could cause the pump to fail on the next startup. Vacuum pumps may also be classified as compressors, since the primary medium being transferred is gas or vapors. A variety of compressors such as sliding vane, piston, liquid ring, and lobe compressors can be adapted to serve as vacuum-type devices. startup, shutdown, and troubleshooting. The basic components of both dynamic and positive displacement pump systems are a pump, piping, valves, instruments, and process equipment as shown in picture. The heart of the system is the pump. It is used to accelerate or add energy to the process fluid. In most operating systems, spare, redundant, pump arrangements are used to permit pump maintenance without shutting down the process. Each plant has a standard operating procedure that should be followed closely during startup and shutdown. Start up and shut down a positive displacement pump. 1. Review the standard operating procedure for the equipment. Each unit will have its own operating procedure for equipment startup. 2. Check the pump driver oil level, cooling requirements, and other specifications. Look for possible equipment damage. 3. Check pump lineup and tank levels. Identify valves that need to be open and shut. 4. Open pump suction valves and fill pump. Be sure all of the valves between the pump and the tank are open. 5. Open pump discharge valves. PD pumps should never be started with the discharge line closed. 6. Recheck pump lineup and start pump. 7. Monitor suction and discharge pressures and flow rates. Be sure pump has adequate suction tank level. Start up and shut down a centrifugal pump. 1. Review the standard operating procedure for this piece of equipment. Each unit will have its own operating procedure for equipment startup. 2. Check lineups in auxiliary sealing, cooling, and flush systems. 3. Check the pump and driver and the oil levels. Look for possible equipment damage. 4. Check pump lineup and tank levels. Identify valves that will need to be open and shut. Estimate NPSH and discharge head. Look at tank levels. 5. Open pump suction line and pump vent valve to liquid fill, prime, the pump. Be sure all of the valves between the pump and the tank are open. 6. Crack open pump discharge valve. Note that if pump is multistage, be sure that the minimum flow system is lined up. In some cases, the pump may be started to press up or take the slack out of the line. 7. Recheck pump's lineup and start pump. When pump operation is stable, open the discharge line valve wide. Adjust discharge valve if the discharge line is slack. Starting into a slack line allows the pump to outrun the suction, damaging the pump. 8. Monitor suction and discharge pressures and flow rates. Check lubrication, bearings, and seals for proper operation. Troubleshoot typical pump problems. If pump is cavitating, there might be high suction temperature, high viscosity, low suction pressure, restriction in line, too much horsepower. Pump speed too high NPSH, small suction. To solve this, lower temperature, agitate suction tank, increase level or pressure, shut down and clear restrictions, decrease horsepower, lower RPM, lower NPSH requirements, increase diameter suction line. If pump is vapor locked, possible cause might be pump not vented before startup or pump is variable speed. To solve this, shut down and bleed off or use a turbine or variable speed motor drive. Specific gravity of product changes, possible cause might be different product composition. The solution is leave alone, will not affect pump capacity. If there is excessive vibration, possible causes may be starved suction, bearings worn, caused by the formation of vapor pockets, pump misaligned, rotor out of balance, usually intermittent, shaft bent, loose foundation bolts, driver vibrating, or instrument malfunctions. You can solve these issues by pinch down discharge valve on pump, shut down and replace bearings, vent pump to re-establish full capacity, shut down and have realigned pump, remove rotating element, check impeller. If passage is clogged, remove foreign material. If impeller is damaged, a new one will need to be installed, shut down and repair shaft, secure pump to foundation, disconnect coupling, and check driver. Locate and correct instruments. If pump fails to deliver liquid, possible causes might be pump not primed, wrong rotation, suction line not filled with liquid, air/vapor in suction line, NPSH insufficient, low level in suction tank or total head required greater than available. To solve these issues, prime the pump, reverse the rotation, fill suction line, bleed off vapors in suction line, increase NPSH, increase level or increase pump size. Pump symbols. Each type of pump can be represented by a symbol. Pump symbols are illustrated in as shown in picture. Pumps can be classified as dynamic or positive displacement. The two most common types of pumps are centrifugal and positive displacement. Centrifugal pumps are dynamic pumps that use centrifugal force and the design of the volute to add energy or velocity to the liquid. Positive displacement, PD, pumps displace a specific volume of fluid, gas or liquid, on each stroke or rotation. PD pumps can be classified as rotary or reciprocating. Rotary pumps displace fluids with screws, gears, vanes, or lobes. Reciprocating pumps move fluids by drawing them into a chamber on the intake stroke and positively displacing them with a piston, plunger, or diaphragm on the discharge stroke. Internal slip is the percentage of fluid that leaks or slips past the internal clearances of a pump over a given time. Centrifugal pumps can operate with 100% slip over short periods of time, discharge valve closed. Positive displacement pumps are not designed to tolerate slip, discharge valve closed. In a centrifugal pump, liquids must be pushed, not sucked or pulled, into the impellers. Suction head is a term used to describe the pressure required to force liquid into a pump. A centrifugal pump must be primed or liquid full before the pump can be engaged. Net positive suction head, NPSH, usually is calculated in feet of liquid. Cavitation is defined as the formation and collapse of gas pockets around the impeller of a centrifugal pump. Cavitation occurs when suction pressure drops below required NPSH. At this point, the liquid vaporizes and forms gas pockets inside the pump casing. As these pockets form and collapse, the pump can be severely damaged. During pump operation, a PD pump should never be blocked in on the discharge side until the pump is turned off. Equipment and personnel can be severely damaged if the discharge pressure relief valve fails to function. That's all, gentlemen. If you like my training course, please follow my YouTube channel Petro Intelligence for more courses. Good day and good luck.